Alrighty. Oh boy, it's a hard one today. Let's see if I can't do this. Um, should I even set up the ending stuff? Well, let's see. There are n children standing in a line. Each child is assigned a rating value given integer array ratings. You're given candies to these children subjected to the following requirements. Each child must have at least one candy. Children with a higher rating gets more candies than their neighbors. Interesting. Return the minimum number of candies you need to have to distribute the candies to the children. So 102, we allocate to the first, second child only, 2, 1, 2. Child is assigned a rating given in the array. So 0 given 1 candy, and because these two are bigger than that, they're given 2 candies. So here, like 1 candy here, 2 candy here, and this one's not bigger, so it has to be the same. What happens if they're the same? Children with a higher rating gets more candies than their neighbors. Allocate, okay, so if they're the same, then you can allocate a lesser amount, but only if it's bigger, then it has to be bigger. Interesting. Huh. Okay. So, how to approach this? It looks like I could probably. Maybe figure out what the lowest one is, what the lowest number of candies is, or the lowest number of ratings is, and then I can extend. So what am I imagining here? If I extend outwards from the lowest, giving more candies for each, then what happens? So like, let's say the ratings are 1, say the ratings are 4, 1, 3, 2. So I start with the lowest and I say I give that rating 1 candy, and then I say the next two besides it are bigger than it, so I say those two get 2, but then I see this 2 here, and I see that 2 there, and then what? I see that 2 there, and I know that the 3 needs to be higher than the 2. I think here I'm envisioning, I think this is true. I'm going to postulate that any minimum rating can be assigned 0 or 1 candy. So anytime I see a dip, like 4, 1, 3, 2, 1, 5, like this one right here, because it's smaller than everything around it, it can be assigned the lowest number of candies. Like there's nothing that is locally that locally prevents it from being just the absolute low. So if I can determine where my minimums are in the set of ratings or in the array ratings, then I can start by giving them 1s, and then working backwards from there. Everything's either a minimum or between minimums. And if it's between minimums, then it has to be like increasing, right? Like I guess it could be flat too. Yeah, I have to determine how I want to handle flat value. So like let's say it's 4, 1, 1, 3, 3, 2, 2, 1, 1, 5. Right, because even flat stuff can be considered kind of minimums at some point. Based on this example, like the second 2 is almost like a minimum for some reason. So how do I want to handle that? So if you're in a sequence of repeating values, the second value is almost like a minimum because it doesn't have anything that prevents it from being lower. But then if it has to be something where it's the ending of a repeating sequence, or it's the middle of a repeating sequence, right? This 5 is considered minimum, but this 5 here would, like if there's a 4 here, like even this 5 is repeating, this 5 is not considered minimum because this 4 is preventing it from, it's causing it to be bigger than that. What if it's something like that? Something that's 5, 5, 5, 6. So this 5 is considered minimum because it's between two 5s. This 5 is considered minimum if it's, yeah, this 5 can be considered minimum if it's, as long as it's next to something that is repeating or bigger. Is that right? So like this 5 is considered minimum, this 5 is considered minimum, this 5 is considered minimum because it's between two 5s. This 5 is considered minimum because it's between a 5. So maybe I should do the negation. It's not considered minimum if there is a number that is smaller than it on either side. Other than that, it's considered a minimum. Is that right? So a minimum is any rating where either neighbor rating is okay, this is where both neighbors are, where neither neighbor rating is below it. So it could be the same, or it could be more, or yeah, it could be more, and it could be considered minimum. Okay, I think that's it, and then I just allocate based on where it is from the nearest minimum. Okay, so let's say, and then maybe I have an array of minimums. So let's say my min indices is going to be kept track of this array. So for every index in range, in range, I'm going to start 0. How do I want to handle the start? Okay, let's say there's n ratings. And for every index in range n, I'll figure out how I want to handle the determining start and end in a second here, but I think it should be something where if min indices, let's say I make a boolean is min is determines whether or not the value at this index is a minimum, and this is going to be neither neighbor is, so not let's say value 1, value 2, value 3 is ratings at -1, ratings at index -1, ratings at index, and ratings at index +1. This I need to optimize this, but not of value 1, neither neighbor is bigger than it. Neither neighbor is below it. If value 1 is below value 2, oh my god, this is just so stupid. Okay, let's say it's previous, current, and after. So if the previous one is smaller than it, or the after one is smaller than it. So if neither of those things are true, then this is going to be considered minimum. So I could do this as if the previous one is greater than or equal to it, and the after one is greater than or equal to it. Previous one greater than or equal to, and that's just De Morgan's law applied to that negation. Previous one is greater than or equal to the current one. Is it greater than or equal to? Previous one is smaller than or equal to, yeah. And then I can say min indices dot append is min. And then here's a hack. Like right now it's going to go out of bounds, or it's not going to really work when x is 0. But I could do a special thing for where I append onto ratings a really big number, in which case when it does index -1 and index is 0, it's going to look at actually index of -1, or index of -1 is ratings at the very end, where ratings at the very end is now a really big number. So like, let's say it's like, 9999 here. So it's going to do 4 compared to 1 and 4 compared to 9999. 4 is, the previous there would be bigger than the current one, 9999 being previous to index 0. But the after one is smaller, so it's going to be false for when that 4 is a minimum, but this generally would work for everything else. Okay, so let me go ahead and print out the min indices and check that this is working. I'll do a test case of, let's say, 4 1 4 1 3 3 3 2 5 5, 4. Okay, so 4 is not a minimum, 1 is a minimum, 3 is not min, this 3 is minimum, this 3 is not, this 2 is a minimum, 5 is not, 4 is minimum. This is perfect, okay. And then I can distribute 1s to the folks that are minimums, and then for the other folks I need to distribute something that's 1 above what's adjacent. 1 above those that are adjacent. How to do that quickly or with 1 pass? Yes, like in theory here, let's say there was a streak. There was like a streak of stuff between 2 minimums, where I had something where it's like 9, 8, 5, 6, 1, and 6, 1. Okay. So the minimums here are just the 1 and this 1. And in theory, this 4 would get assigned a 2 because it's like, 1 bigger than the 1. Now the 6 here could be assigned a 3, but then the 6 here could be assigned a 3 because it's bigger than 4. I guess what is the issue here? When it's increasing, it has to be bigger. Yeah, so I guess the issue would be something like 6, 5, 2. So if it's increasing, then it needs to be bigger. Interesting. So I would assign the 4 a 2, I would assign 6 a 3. Maybe I don't assign 5 and 2 because I don't know how big they need to be. Actually, I don't even know if I can do that. Maybe I need to assign the 4 and the 2 simultaneously, and then collapse it. 4 is assigned 2, and the 2 is assigned 2. Because the issue here is, like, let's say it was 4, 6, and then 5, 4, 3, 2, 1. So in theory, if I do greedy and assign 1, 1, well, that's not greedy, but the minimum is assigned to 1. The adjacent one here is assigned 2. The adjacent one there would be assigned 3. But then 3 is not big enough to go down towards this next minimum. So there's a couple ways to maybe approach that issue. One is to do 2 passes, and I force this thing, like I do a 4 pass, and like say this is 4 is going to be at least 2, 6 is going to be at least 3. Well, 4 would be exactly 2, 6 would be not necessarily 3, but then I do a second backwards pass and say this 1 is 1, this 2 is 2, this 3 is 3, this 4 is 4, this 5 is 5, this 6 is 6, in terms of how many candies get assigned to each. So I do a forward pass, going for increasing amounts of the forward ones, and then a second pass for increasing amounts of the It's going to be quickish, but it's not necessarily the fastest, I think. But there might be more efficient ways to do this, but I think this is going to be correct. So let's say candies is going to be the assigned to each. So I can say, let's say the current is 1. I need to start where my mins are actually. Like if I need to start where my first min is in order to figure out. But then if my first min is at, okay, I think maybe for every index in range n, I need to find out where my first min is. Maybe I start with min index equals -1. I need to know where my first min is, and I need to know where my last min is. I need to know where my first min is, and I need to know where my last min is. Okay. I think I need, like, first min is going to be this, and last min is going to be, anytime I append is min, if it's a min, then last min is going to be set to this index, and if if I haven't set first min, then I want to set first min. If first min equals -1, then first min is equal to this index. Alright, let me double check this works. Print min indices, first min index, and last min index. Because I want to do the loop, the other loops, where I know where these things are. Okay, yeah, so first min is there, last min is there. First min is at 1, last min is at 0, last min is at 2. Actually, 1, and last min should be at 7. Yep. So let's say min index is going to be starting with the first min for every index in the range starting with min index plus 1 to n if okay, so it's if the current rating, if min indices of this index is true, if this is a min index, then I need to reset the min index. This is like, I want to go through the array and for every later index, kind of see how far away it is from the current min index, or current kind of left side min index. So min index is going to be to this index, else as long as this number is bigger than the previous index, as long as the value here is on the upward swing going left to right, so like going from 1 to 4 or 4 to 6, that means it's going in the upward swing, then I can assign candies to this spot. Actually, maybe I can say if it's a min index, actually maybe I should start with the min index. I mean, if it's going downwards, then does it really matter? If it's going downwards, then I just don't do it. Yeah, if it's going downwards, then it's not a minimum. Huh. Maybe I don't need the first one thing. So I could say maybe for every index in range n, if this index, if the min indices of this index is true, then I can assign candies, one candy to this person. Else, if the value's increasing, so if the ratings of this index is greater than the ratings of the previous index, then candies of this index is one more than the candies previously. Does this work? So I think this works in general. I think this works in general. So does it work for like something where it starts out with 4? So because this is false and ratings currently has infinite at the very end, so 4 is not bigger than the previous, so it's not going to assign anything there. Yeah, I think this is actually fine. Maybe I don't need to keep track of my first and last min. And then I do need to go the other way around because it's not assigning anything. So it's not assigning anything to the 4 rating kid. So if I say if index in range of n minus 1, negative 1, negative 1, and here this is a case where it might bump up into something that's incorrect, like 1 gets assigned 1, 4 gets assigned 2 candies, the 6th kid gets assigned 3 candies. Now if I go backwards, the 6th kid needs to be assigned something bigger than the 5th kid. So I was being greedy on the first approach, but now I need to bump it up on the second approach if it's like a maximum, pretty much. On the second approach, I don't need to set the so on the second approach, going right to left, I can just say if the ratings of the index is greater than the ratings of the one after it, then candies of this index is equal to the bigger of candies of this current index. So whatever is currently there due to assigning it. I think this should actually be I'm going to assign 0 to everything initially. So whatever's currently there for candies of index plus 1 plus 1. So whatever number of candies I give to the kid after it, one more than that. Assuming this kid has a higher rating. And then I just return the sum of all the candies assigned. Alright, let's go ahead and actually print out what this thing is doing for now. int is not a scriptable object. This should be min indices. Okay, so I assigned the first kid 2, second kid 1, third kid 2. Okay. 1, 2, 1, good. So this one's 1, this one's 2, 2, 1, 2, 1, 2, 1. I think that's right. 2, 6, 2, 4, 6, 8, 12. Okay. And then I can say return the sum. No, return the sum candies. I assume there must be some test cases. Oh, okay. Okay, so seems like I got a solution. Let's see if I can optimize this. So I don't think I need the first min or last min. Do I even need to know where my min indices are? Could I determine that on the fly? I think adding the infinite at the end is fine. I wonder. So this is all this min indices stuff is just to do some pre-processing. But can I do that processing on the fly? So I don't need to create this array. I think that's what's causing this to be slower than the other solutions. I mean, these solutions are pretty darn fast, right? 27 milliseconds versus like 10 milliseconds. Not a lot of time. Obviously, this is all O-of-N stuff, like single pass solutions. The other thing is maybe I don't need to actually have a candies array. I think the candies array is very minimal. I think it's just the min indices that were. Could you do it without the candies array? I mean, maybe you can do it with a set of min indices rather than a min index that has size n. How big is n? N is 2000. Or 10 to the third is 20,000. I guess that's pretty large. Yeah. Okay. So let's try to think about how I might do this with an on-the-fly approach. So for every index going forward, if it's a min index, so I can just use this if statement here. If the I could maybe say that if I wonder, can you use a double inequality that is not fully correct? So let me try something. Can you do something like if 5 is bigger than 1 is less than 2? Maybe I can use a variable here. Oh, oops. Can't even do print true. Huh. I wonder, and what if it was something like that? Okay, so Python is actually quite neat with these inequality expressions. Okay, so I could say here if the ratings of index minus 1 is greater than or equal to ratings at index is less than or equal to ratings at index plus 1, and candies is assigned to 1. Otherwise, if the ratings currently is bigger than the ratings before it, then it's assigned. Yeah, I think this is fine. And then I do a second pass. Okay, I think this would work. So I don't need to calculate min indices at all. I don't need this anymore. And I can comment this out now. Alright, let's see if this speeds up the solution. Well, 7 seconds faster, but still not very fast comparatively. Can I do it in 1 pass rather than 2 passes? If ratings is bigger than the ratings after it. Otherwise, if ratings... if it's not bigger than... If ratings is minimum, then set the candies to index 1. I wonder... I mean, could it be that it's... Could it be that... Could you just keep track of where the mins are? Could you just keep track of where the mins are? Can you figure out where the mins and maxes are? And then do a straight formula from there? Like, I guess this is a lot of checking of stuff. If you know where the mins are, and you know where the maxes are, so if you go for min, for every min there has to be a max. So you can alternate between maxes and mins. For every min there's a max. And then you just alternate between maxes and mins. Okay. So if you kept track of just that, so you start by tracking your mins in an array, and then you have a sum to your maxes index. So I guess that could be 1 pass. No. What am I thinking here? I'm thinking like if your mins are indices. Okay, so those are the numbers, and the indices are 0, 1, 2, 3, 4, 6, 7, 8, 9, 10. Maybe I don't have this last one. So the mins are index 1, index 3, and 9. and max indices are at 0. This is index 5. So every time you see a max index, it's going to go down to the next min index, and it's going to just be like 1, 2, 3. And every time you see a min index, it's going to go up to the next max index. I can't see how this is all that much faster. Might be slightly less comparisons. It might be 1 pass rather than 2 pass. So you do 1 pass, figure out where the mins and maxes are, and based on where the mins and maxes are, you can deduce what the sum is. Like in theory, if you're given just two arrays like this, you don't have to do, the second pass should be a lot faster. Huh. Theory. The first number should always be a max or min. So go 0 to 3. And your maxes, your mins are always 1s. And your maxes will be, the max value should be on one side, not both sides, I guess. Like the max at 6, it can be accounted for as increasing from 0 from this 1 to 6, or it can be increasing from the 2 to 6. And I should be using the 2 to 6 because that's the longer distance to get to that max, so that means there's more candies that must be assigned. Huh. Man, I'm on a losing streak in terms of my my quality of acceptance runtime. How are these other kids doing it faster than me? Yes. Would like to get rid of this max deal. Because it's an extra if statement each time that you do this loop. Every time you need to increase the rating. Ratings is bigger than the kid after. You have to get one more candy to that kid. Max of candies or max of previous one more than the previous one. Alright, I think I'm gonna call that. I don't know. Okay, I'm curious what the actual fast solution is. Start by giving one canyon. It's strictly, you don't need to worry about I see. It's more greedy. You don't need to worry about mins assigning ones. You just assign everything one. So here I forced. Wow, that is. I mean, they do still do it in 2 passes, so I guess I feel fine about not trying this min-max deal. So basically what they did was they just said if the ratings is bigger than the thing after it, or the ratings of the current index is bigger than the ratings before it, then just give it one more than the one before it. And then do that on the second pass, but on the second pass also guarantee that the second pass going backwards, but guarantee that you're giving it higher than what was given on the forward pass. Let's see. Alright, so I guess guess this is a more efficient way. And this is like n is the length of ratings. I think ratings.append the infinite thing is fine. Makes it one less thing to worry about. Candies is assigned 1 to everyone first. And then for every index going forward, then if the ratings of this one is bigger than the ratings after it, bigger than or equal to, or bigger than the one before it. Yeah, it's only bigger than the one before it. And candies of this one is equal to candies of the previous one plus 1. And then, I don't know why this, didn't use this semicolon. And then going backwards, it's like for every index in range, n minus 1, negative 1, negative 1. The ratings of this one is bigger than the ratings of the one after it, going backwards. Then candies with this one is equal to the maximum of candies of this one currently, of candies of the one after this plus 1. Because this one could be set higher based on the forward pass. And this returns some candies. Alright, I think this is correct. And I guess this is faster. Well, maybe adding this infinite thing is making it slow a bit. And this is the original approach I had. Okay, so I think in general they're very similar. This is obviously more optimized. This definitely didn't seem like a hard problem, or there were a lot harder problems labeled as medium and hard previously. Summary. I'll describe my original thing, which is go through, note that all minimums have a low minimum ratings, local minimums, have are always assigned one candy, and you can assign candies in two passes, like a forward pass and a backwards pass, where in each pass ensure that the candy assigned is based on either increasing rating or decreasing rating. Guarantee that is based on if rating is higher than neighbor, candies assigned is one higher than neighbor. So if you do the forward pass, so for forward pass, if rating is bigger than rating to the left, index -1, candy assigned is one more. So like candies of I is equal to candies of I -1 plus 1. When doing backwards pass, make sure that candies assigned is maximum of what was assigned by forward pass and by looking at ratings backwards. So yeah. And then time complexity, this can be open. Doing two passes to and obviously then sum up all the candies assigned. And obviously before you assign the candies, you create an array of assigned candies to each index. Doing two passes to determine candy assignment based on local comparisons of ratings. And then space requirement, this can be O of n to have array of candy assignments. And obviously you need that to keep track of both sides of it.